Hello, my dear students. I wanted to briefly cover a little bit of our first topic as we begin to study atomic structure, and that is just a historical perspective on the atom and atomic structure. You have the accompanying PowerPoint lecture notes and information in your class stream, but I did want to very briefly, especially for our virtual students who didn't get to interact with me yesterday, discuss what's essential in this particular topic and go on and answer one of the questions from the accompanying assignment. So, as we talk about early models of the atom, people didn't really know or understand much about the atom. We go back to ancient Greece first, but I will say we need to define an atom. I always say an atom is the smallest particle of matter that retains all the properties of that matter. But perhaps a better definition is this one here. An atom is the smallest particle of an element that retains its identity in a chemical reaction. I just want to discuss what's essential. I don't know why we do this, but we tend to also always present a historical perspective and what was wrong with previous models rather than just telling you the model that fits and is correct. But it all goes back to Democritus, and we can thank him for several things. He lived to be quite old. In fact, he lived to be about 90 years old from, I want to say, 460 to 370 BC. Of course, you don't need to know those times and dates, but I want you to know that he preceded Plato and Socrates and Aristotle, and he said that atoms were small, indivisible, indestructible particles. And he coined the term atom from the Greek atomos or atomos. We don't know how it was pronounced because it's a dead language, but he just had this as a theory as to what atoms were and how matter is composed of smaller and smaller pieces. What's essential here is that he did get right is that even though the atom today is not indivisible, we know we can split the atom, but we can only split it into subatomic particles, as we'll hear about in the next section. At a certain point, you get to a particle that is still an atom of the element you're studying, and still retains the properties of that element. But if you break it apart any further, it is no longer that material or that element. So, I won't say improving, but expounding or expanding on that theory, John Dalton, using the scientific method so that his theories of atomic structure could be experimentally tested, came up with his own theory of the atom, Dalton's atomic theory. We're going to give a lot of credit to Dalton and his research. He was an Englishman who lived from in the early 1800s, 1766 to, I want to say, 1844. But he gave us the following theory, and that is that elements are composed of tiny, indivisible particles called atoms. We know we can divide them up, but we can't divide them up into smaller atoms. We can only divide them up into subatomic particles. You can't have half an atom or a fourth of an atom or a third of an atom. Once you get to a single atom, it cannot be subdivided or, any further. So practically and functionally, it is still indivisible. And I learned that, all the atoms of a given element are the same, and if two atoms are not the same, they are different elements. It's perhaps more eloquently and more correctly stated here that atoms of the same element are identical. And we're actually going to qualify that um, later this week or early next week when we talk about some subtle differences between atoms of the same element called isotopes. But, as we progress and learn more, we refine our theories. But Dalton's theory is still essentially and practically a good fit for today's understanding of the structure of the atom. Just a little incomplete. We also know that atoms, and Dalton's theory said atoms can physically mix together. For example, combining carbon and iron to form steel, or brass and copper and zinc to form brass, or they can combine in simple whole number ratios, small whole number ratios, to form compounds. For example, we have little blue balls here that are hydrogen atoms and larger red spheres that are oxygen atoms. Those come together in the ratio of 2 to 1, H2O. The one is understood, so H2O1, to form water. And Dalton also, studying reactions, postulated this, and that chemical reactions occur when atoms are separated, joined, or rearranged. And, this is true today. When we look at reactions, those atoms involved in those chemical reactions still follow Dalton's atomic theory. So, Dalton's modern view, or much more modern view than what had been held previously, gave us a good starting point for our understanding of atomic structure. I will also say briefly that you can't truly see atoms, but you can see their outlines and their shadows using an instrument called a scanning tunneling electron microscope. Here's an example of some iron atoms. You can only, with a scanning microscope, only see the surface of a sample, and you can get the outlines of atoms, but it's not a true picture of what the atom structure is. It's more just like a shadow or a reflection of the contours of an atom. So I wanted to answer one of the questions on the section review briefly. Here are some, I guess, the obligatory sample questions. Of course, people all recognize Plato, Aristotle, and Socrates for their contributions to government and science and biology and philosophy and education, but it was Democritus, of course, who is credited with describing the atom in the most correct way of those philosophers, and Dalton's theory improved on it because he used the scientific method such that experiments could be used to test and verify his theory, or improve upon it, or modify it, because that's the nature of science. And finally, individual atoms, of course, I don't even believe in truly accurate terms that they can even be observed with a scanning tunneling electron microscope or STEM, but certainly their form and outline can be. So I wanted to briefly answer one of the questions, and that is, if you look at it, asked, this is your answer to one of those questions. It asks how many copper atoms in 1 meter if you line them up side by side. And you can look up the atomic radius of copper and you can make this calculation, but let me simplify it for you and just say if you have 100,000, not 100,000, 100 million copper atoms, they take up a they would line up and have a distance of 1 centimeter. And this is 1, 2, 3, 4, 5, 6, 7, 8. This is 10 to the 8th in scientific exponents. Your math teachers would want me to write 1 or 1.0 times 10 to the 8th. But 1 times anything is anything, so I'll keep it simple. 10 to the 8th copper atoms per 1 centimeter. And we know that there's 100 centimeters, in a meter. So that would be, 100 is 10 to the 2, so that would be 10 to the 10th copper atoms in 1 meter. So that's your answer to the last question. I do want to say, if you look at a copper penny, a cent, a U.S. cent, it has about 2.4 times 10 to the 22nd atoms in it. And if you do the math, this would be 10 to the 13th atoms per kilometer. If I take our answer for our question, this is exposition. I'm trying to make a point here. And that is, if I have 10 to the 13th atoms per kilometer, and I have 10 to the 22nd atoms, 10 to the 22nd divided by 10 to the 13th is equal to 10 to the 9th, or 1 billion kilometers. So the atoms, the copper atoms in a single cent, in a single penny, lined up side by side in a wire 1 atom thick, would stretch for 1 billion kilometers. And if you want to do the conversion to something more standard, that would be around 600 million miles, or a distance from the Earth past Jupiter. So that is there just to prove a point, and that is atoms are extremely small. They're extremely, extremely small. 10 to the 22nd of them in a single copper cent, but they're extremely numerous. So they're very small, but extremely numerous. We have to work with very small dimensions, and we have to work with very large numbers in chemistry. So that's the top part of the slide is the answer to your question. And I hope that helps you get a better score on your assignment. That's all, and we will see you in the next video.